Hello, thanks for watching. I'm Brian Bailey. I'm an assistant professor in the Department of Plant Sciences at UC Davis. And for this talk, I'm going to talk a little bit about some of the 3D plant modeling tools that we've been developing and their application in agricultural computer vision. This work is in close collaboration with Mason Earls, also at UC Davis. And he'll be giving a talk focusing more on the technical details of some of this computer vision work, and I'll share more on the modeling side, which is the part that I've been working on. So first, I just wanted to talk a little bit about the modeling tools in general and kind of the original motivation for developing these tools. When I came to UC Davis, I originally set out to develop a three-dimensional plant modeling framework that would essentially allow you to simulate any decisions or design practices that a grower might use, with particular focus on perennial cropping systems. So just like in engineering design, we often have some ideas or questions that we may want to address in agricultural systems. And in order to test those ideas, we do some type of experiment or prototyping. But in perennial cropping systems, this can be quite costly and take many years to even decades to carry out a full field trial or experiment to test those ideas. So just like in engineering design, having essentially the analog of a 3D CAD model for agricultural systems that can allow us to quickly iterate across different designs in an in silico environment can help to really speed up the innovation process in general. So that's kind of what we originally set out to do, and to accomplish that goal, we've developed a software framework called Helios, which is a generalized 3D plant modeling framework that couples different models, creates different 3D geometries, and then handles the data and different computations associated with carrying out those models. So Helios is a C++ API. If you're unfamiliar, that means that you essentially write your own code in C++ and then call different libraries and functions in order to, say, generate a 3D canopy or run through a radiation or photosynthesis model or something of that nature. And we keep it pretty high level in terms of the API. We don't really go super deep into some of the nitty-gritty features of C++. It's pretty basic object-oriented programming, at least on the at the higher level. It's gotten pretty complex. It's about 500,000 lines of code or so, and it's pretty well documented with hundreds of pages of documentation. Essentially every plugin and function is documented, and then we have different tutorials and things like that. It's publicly available via GitHub, and we have a paper that kind of describes the general idea with some different use cases. So Helios has a number of different model plugins, from radiation transfer to the energy balance solution, which can get you things like ET, photosynthesis, stomato-conductance, soil transport, procedural generation of plant geometries. So this means that we generate essentially random perturbation or random plants with perturbations of the different geometric parameters, a visualizer for photorealistic rendering. We have plugins for dealing with LiDAR data, as well as creating synthetic LiDAR data, which I'll talk about, as well as various others that are in different stages of development. So I don't have time for, nor do I think that it's prudent to talk about each of these plugins in detail, but I'll just talk quickly about the radiation transfer model because it's relevant to some of the computer vision applications that I'll talk about just here in a minute. So we developed a new ray tracing based radiation model for both shortwave and long-wave radiation transfer. A lot of the novelty and innovation is more on the long-wave transfer side. Getting long wave emission correct in these very complex geometries is important, especially when you couple with other models, such as if you want to determine temperature or things like that through the energy balance equation. So we developed essentially a new method for long wave ray tracing that's a backward ray tracing method. So it ensures that every element is properly sampled and that you get consistent results in that it satisfies the second law of thermodynamics, which is something that a traditional ray tracing model doesn't do. And I like to show this somewhat tongue-in-cheek visualization. This is the well-known Stanford Dragon model. It's pretty complex. It has highly skewed and very small elements. And this is a long wave emission simulation that just shows that we get a very smooth radiation field, which is important for the reasons that I mentioned. And it just demonstrates the generality, meaning that we can take any arbitrary polygon mesh and run it through the models. I'm sure probably most everyone in this audience is familiar with GPUs, but I just wanted to mention quickly that we implement many of the models, including the radiation model, on the GPU in order to accelerate calculations, which vastly speeds up the throughput of model calculations. These are just a few sample visualizations. We can do artificial lighting, different crops, arbitrary geometries. Again, we can just generate any sort of mesh and then run them through these various models. We've also done quite a bit of work in terms of measuring plant structure, specifically through LiDAR. So again, probably most all of you are familiar with LiDAR. But one of the challenges when we want to use LiDAR data in order to, say, provide inputs for these 3D models is that, of course, the LiDAR gives points, not surfaces. So we need, for a 3D model, things like surface normals, areas, things of that nature in order to run them through the models. Just the points themselves are not super useful. So we developed a number of algorithms for processing raw LiDAR data into inputs that are relevant for 3D models. So we developed an algorithm for determining the leaf angle distribution of plants. Generating thousands to tens of thousands of measurements of leaf angle rapidly. It basically uses a triangulation algorithm, but you can't just apply a standard Delaunay triangulation or something like that when you have these small disjointed objects, because they'll tend to connect up and create a lot of triangles that are essentially unphysical, that are connecting adjacent leaves. Our approach also allows you to properly weight each of those triangles or surface normal measurements to allow us to calculate an unbiased leaf angle probability distribution function. If you don't account for things like the angle of the scanner and other things within your triangulation, then you can bias toward elements that are more perpendicular to the direction of the scanner. We've also developed a leaf by leaf reconstruction approach. So the problem with reconstructing large plants such as trees is that a large fraction of the leaf area is occluded from view of the scanner. And so that means that just doing a regular leaf segmentation is only going to reconstruct a certain fraction of the total leaf area. So we developed an approach that combines the ability to, or our capabilities associated with the leaf angle distribution measurement, as well as other algorithms for determining the leaf area distribution. Helios can also generate synthetic LiDAR data sets. This is useful in terms of not only verifying or validating the different algorithms, but also, as I'll talk about later, in terms of generating synthetic data sets to couple with computer vision or machine learning type of models. So we've developed different techniques for running our algorithms through these synthetic data sets where we know everything about the geometry of interest, so that we can quantitatively test their ability to do essentially what we are hoping that they'll do. So these are just a few visualizations of putting a lot of these pieces together. This is an almond orchard that we LiDAR scanned, applied the reconstruction algorithm, and then are running it through different 3D models, the radiation interception, energy balance, stomatal conductance, in order to predict for every leaf in the canopy the water flux or transpiration flux in this case, but we could overlay any number of other data layers that are calculated within the model. And this is just a 3D visualization of an almond orchard, so showing the full irrigation system, as well as overlaying different data layers and manipulating the geometry, et cetera. Okay, so that was just a very quick overview of Helios and the 3D modeling system in general. So I'll shift gears into the actual computer vision and machine learning type of approaches that we've more recently targeted in terms of applications of the 3D models. So I'm sure this is common knowledge for nearly everyone watching this video, but of course, machine learning models often require supervision that can be quite time consuming, especially when you need hand labeling, when there's lots of things to label, or very complex objects that can be difficult even for a human to recognize and label. But just like in a wide range of other fields, we've been working on using models to create simulated data that can be used to provide synthetic ground truth data for machine learning types of models. So we've started with RGB imagery. So the visualizer plugin in Helios is able to generate these realistic renderings. And we can go in and auto label every single pixel within that image, because we know if it corresponds to a fruit or a leaf or the sky or the ground or anything like that. So we can rapidly go in, label every pixel in the image. We can also look at non-occluded labeling as well. So we can remove all other elements except for each one that we're labeling and write out those to file as well for training of a neural network. And then we can apply this to real images to make relatively good predictions, even when the model has never seen a real vineyard in this case. So some of the unique things about our software is that we implemented a scheme to greatly improve the speed when you have very complex images with lots of different labels. So when you're rendering each of the individual elements with no occlusion, you can run into efficiency issues when you have to write out lots of images to file and do lots of renderings. So we implemented some efficiency gaining approaches in order to speed this up relative to other software available that can do this as well. We also use procedural plant generation models, as I mentioned earlier. So this allows us to randomly vary geometric parameters so we can get variation. We're not just sort of using static models. So this allows us to cover a wide parameter space as we're training the models with this synthetic data. And Mason will talk about this in much more detail if you tune into his talk as well. But a postdoc that's been working in his lab in collaboration with my lab has been working on using Cyclegan to generate these synthetic real images based on Helios auto-labeled images. So you take the auto-labeled simulated image and then combine that with real images to get this essentially auto-labeled synthetic image that looks real because it's based off of real images. So as I mentioned, we started with RGB imagery, but I think a lot of the real power in integrating with Helios comes in being able to simulate other sensors rather than just an RGB camera. So I mentioned the radiation model, which allows us to simulate multispectral imagery. So we can simulate the full radiation field across any arbitrary waveband in order to simulate what a multispectral camera or other type of spectral sensor would be producing. As is illustrated in this visualization, we can also simulate thermal imagery. And I mentioned generation of synthetic LiDAR data. So we can do a synthetic LiDAR scan of the scene. We can do this for both discrete return as well as full waveform LiDAR instruments as well. We haven't worked on this yet, but it's would be pretty straightforward to include a solar-induced fluorescence as well within the model. And we have plans to do so in the near future. So again, I think the capability to simulate a lot of different sensors and critically what the effect is of varying the underlying physiological or biophysical processes that are happening that influence these measurements. So we could, for example, vary parameters associated with a stomatal conductance or different water use related parameters, simulate their effect on, say, thermal imagery in order to train a model. So these are things that we could never really measure with high throughput. You couldn't measure these different physiological parameters directly with high enough throughput you could use to train a neural network, but being able to simulate those across a reasonable parameter space and their effect on these different simulated sensor measurements can really generate a very powerful data set that can complement maybe a much less robust actual physical ground truth data set. And I just wanted to mention one other sort of application that's relevant. There's a student in my lab working on mechanical harvester design. And I think there are opportunities to combine this with computer vision type of approaches to, say, guide robotic arms or guide harvesting equipment. So we're able to model the structure of the plant, calculate things like interference, occlusion, things like that in order to develop models or to test various ideas for mechanical or robotic harvester designs. All right, so that was just a very quick overview of some of the work that we're doing. Feel free to contact me if you have any questions, and I wanted to quickly acknowledge my funding sources and again mention that our software is in a publicly available GitHub repository if you're interested. So thank you very much for watching.